Alright, this is LeetCode 235, lowest common ancestor of a binary search tree. So, given a binary search tree, find the lowest common ancestor node of two given nodes in a binary search tree. So, they give us a definition of what lowest common ancestor is, and it's basically defined as between two nodes P and Q at the lowest node T that has both P and Q as descendants. And then we allow a node to be a descendant of itself. So it's kind of a mouthful. Let's go ahead and look at the examples to see what that really means. This is important here, but let's look at the example one. So, so here's our example one. We're given this binary search tree, right? Basically meaning that everything to the left of a node is less than, and everything to the right of a node is greater than. So it's kind of like in a sorted order. It has somewhat of a sorted order where we can rely that if we go to the left child, it's going to be less than the current node, and if we go to the right child, it's going to be greater than the current node. And if we're given P as being 2 and Q as being 8, then the output would be 6. Why would that be the case? Well, because we're trying to find the lowest common ancestor between these two nodes, P and Q. So here is our node with value 2, and here's our node with value 8. Well, the lowest common ancestor, if you can think of ancestor as being like these two nodes are almost like children of this node. So this can be thought of like the parent node. This is like the parent node, and then these are descendants. You can think of this being like a child, a real life child of this node, and then this is like another child of that node. So this is like the left child. This is like, you can think of it as like a family tree. So this is what the output would be, because this is the lowest common ancestor. Yeah, so let's go ahead and scroll down to the next example. So with this example, it's a little more difficult. So we're given P and Q to be 2 and 4. So 2 and 4 happen to be on the left subtree of this whole tree. So they're on this side. So the output would be 2 because, as we said in the prompt, a node can be a descendant of itself. So if we're looking for 2 and 4, 2 can be a descendant of itself, and then 2 is also is a parent of 4. So 2 is a descendant of, actually no, the opposite way. 4 is a descendant of 2. So this satisfies what we're looking for, and that's why we would output this value. Cool. Yeah, and then it's also given that all node values are unique, so that's nice. Okay. Yeah, so how could we actually solve this? So so they're giving us a binary search tree, right? So they're going to want us to do something. They're going to want us to leverage the fact that it's a binary search tree, and that we know that the left children are less than the current node and the right child is greater than the current node, right? So what we can do is, let's run through like an algorithm, right? So we're going to say our P and Q are these values, right? Okay. So what we're going to do is we're going to say, okay, how does 6 compare to our how does 6 compare to our p-value, or how does our p-value compare to 6? So our p-value is 2, and then our current node, this is our current node right here, current, this is going to be current right here. How does this compare to that? Well, 2 is obviously less than 6, our current node, so we know that P is somewhere over here, right? We know that P is somewhere over here in this side of the tree. It's not going to be over here because we know that everything over here is greater than 6. So we wouldn't want to spend time looking over here because we know that 2 is not going to be over there, or P value. Okay, what about Q? How does Q compare to our current value? Well, Q happens to be 4, and our current value is 6. So how does that compare? 4 is less than 6, so we know that Q, or what it's currently set to, which is 4, is over here. So we know that we can just disregard these nodes. This whole subtree, this right subtree, is out of consideration. And then this is also out of consideration because it's not equal to. Okay? And then we're going to go ahead and we're going to move our current pointer to our left subtree because we did these checks to see how does P and Q compare to our current value, which is our current node value. So now our current value is going to be here, and we do it in a different color. Now our current is going to be here in our second iteration. Okay. How does P, which is 2, compare to our current value, which is 2? Well, we're actually at our value, right? 2 is equal to 2. So that's good. We know that we found one value. And then how does 4, which is Q, compare to our current value, which is 2? Well, 4 is greater than, right? But do we actually, now we have to think about this, do we actually even need to compare this once we found a node? If we know that in the previous check, in this check over here in green, right here, what I'm circling in purple right here, this text in green, we found that P and Q were in this left subtree, right? So, and then we found 2. We found P and current matched up, so 2 and 2 equal 2, right? So we found one of our values, which happened to be P. And since we know that Q is going to be in this subtree, which is 4, we know that 4 is going to be somewhere over here. It happens to be right here, right? But we know that it's going to be in the left subtree. So since we found our value, our P value, or it could be Q, it doesn't matter. Since we found it, we know that we can just return this value, right? Because this can be a descendant of itself. And we know that 4 is going to be somewhere down here. 4 can be over here, 4 can be over here, or 4 can be over here. We just know that it's going to be somewhere over here, right? It's going to be one of these values, or it can be any of the subchildren below it. It just happens to be right here in this problem. So, yeah, and then we can just return 2. All right, so let's try to write the code for this solution. So, we're gonna need a loop, right? We're gonna need some certain loop, and typically with these node data structures, you usually use like a while loop. I think you can get away with using a for loop, but honestly, I think the while loop is a little easier to use. So let's think of what our condition is going to be. So it's going to be while. Oh, give me a second to turn on my keyboard. Okay, so while. What's our condition? Well, we're using our current value, right? Which happens to be actually, I think we can just use our root. This can be substituted for the root variable. So what we want this root value, or current, which is, they're both the same thing, but we want it to iterate through all the nodes, right? And eventually it's going to get to, eventually these children, they're not, it doesn't say it here, but these children, or these nodes have children set to none. So the leaf nodes have none children, right? Because this is the default value. If you don't give it a left and a right subchild, you get, it just has none. So what we can do is basically say while root does not equal none. I think you can simplify this to just say while root also, but I think just to be a little more explicit, we can just write it this way. So while root does not equal none, what are we going to do, right? So previously, kind of, what were we actually doing? I think we wanted to see if P and Q are in one subtree, like to decide if they're in the left subtree of our root value or if they're in the right subtree of our root value. So let me erase this. What I'm saying is that P and Q are 4, right? Or P is 2 and Q is 4, right? So starting from this root value here, this is root, we want to decide, does P and Q belong on this side of our root value or does it belong on this side, right? And then we divide this tree in half. Does it belong on the left side or does it belong on the right side, right? Okay. So we're going to say, and how do we actually do that? We can say if P dot value or val is less than root dot val, and what is it, Q dot val is less than root dot val, then we know that P and Q are on the left side because it's these values, P and Q values, were less than our current value. So this is true because we're using a binary search tree. If we were using any other sort of tree, then we couldn't rely on this fact. Okay, so then we can just say, now that we know P and Q is on the left subtree, what are we actually going to do? Well, we can just reassign root to be equal to root dot left, right? Because we know P and Q is going to be in the left subtree. It's going to be somewhere down here where my mouse is going. Somewhere right here, these nodes. Okay, otherwise we have like an LF and just say LF P dot val, just basically the opposite of this. So P dot val is greater than root dot val and Q dot val is greater than root dot val, basically meaning that if P dot val and Q dot val is greater than, which would mean that it's on the right hand side of this subtree, meaning P and Q are somewhere down here, given like maybe the instance where P was 7 and Q was 9, then we would want to reassign root to be root dot right, because we know that P and Q is somewhere down here, right? And we would just want to reassign our root value to this value. Okay. Otherwise, if both of these conditions don't pass, if this isn't true and this isn't true, then we have the condition where we found our P value or we found our Q value, right? Or we found our current node is in between our P and our Q value, so we found our lowest common ancestor. Otherwise, meaning we can just return root. Cool, and then yeah, I think that works. Yeah, okay. Let me go ahead and try to access the time and space complexity. Space, I believe, would be O of 1 because we're not using any extra memory, we are using some variables, right? But these variables aren't going to scale as our input size grows, so it's going to be constant. And then our time, this I believe would be, well, so let's say that the total amount of nodes in our binary search tree was like n, right? So n represents the total amount of nodes. Then because we're using like this kind of divide and conquer situation, like if you've ever done any binary search problems, typically that's like log n time, because you're dividing it by 2. So I think this time complexity would be O of log n time. And then it's good to remember that this log is base 2. So this basically we're dividing the number of steps by 2 each time, because we're basically choosing left or right based on where our Q and our P value relates to our root or our current value. And that lends our time complexity to be here and our space complexity to be here. Cool. Thank you for watching.